Welcome back to the deep dive. I hope you're ready to switch gears today. Usually we take one specific topic, maybe it's a historical event like the fall of Rome, maybe it's a tech trend like generative AI or, the history of coffee, and we drill down.
We go vertical.
We go vertical. We dig until we hit at the bedrock of that single subject. But today we are doing something, well, completely different. Today we are going horizontal.
We are indeed. We're zooming out. We're taking the panoramic view.
We're looking at the world through the lens of what might be the ultimate generalist tool. It's a format that almost feels, retro in the age of Google and instant answers, but there's something so undeniably powerful about it.
Oh, absolutely.
We're talking about the encyclopedia. Specifically, we have this massive stack of material here from the DK Encyclopedia. And I have to say, just holding this material, it feels heavy, literally and, well, metaphorically.
It does. And I love this choice for a deep dive because an encyclopedia does something that the internet, for all its power, often fails to do. The internet is an engine of specificity.
Right.
It gives you exactly what you search for. It's an algorithm of confirmation.
Right.
If you search for, say, how long do frogs live, it gives you a number. It doesn't tell you about tectonic plates unless you specifically ask for it.
Right. The internet is a sniper rifle.
Yeah.
The encyclopedia is a shotgun.
Exactly. An encyclopedia gives you context. It forces you to connect dots you didn't even know were on the same page. It creates serendipity.
It's the original hypertext, isn't it? You open it to look up, the atomic weight of gold, and you just scan the page, and 20 minutes later, you're somehow reading about the mating habits of tree frogs, and then you flip the page again, and you're staring at a map of the Atacama Desert.
And the magic moment is when you realize they are actually part of the same system, and that, I think, is the mission for this deep dive. We aren't just reading random facts. We're trying to traverse the spectrum of knowledge contained in this source material. We want to see how the microscopic world of atoms and cells actually informs the monumental world of continents and oceans.
Okay, so just to give you a roadmap, because we are covering a lot of ground today, we're going to start with the foundation. How we actually know anything is true? That brings us to science and the scientific method. Then we're going to zoom all the way in to the biological level. Frogs, cells, all the gooey stuff of life.
The good stuff.
Then we pan back out to the oceans, the deserts, and finally, the human map. The borders and cities we've plastered over the top of it all.
From the microscope to the map, it's an exercise in scale, really.
And honestly, the hook for me here is the randomness. I was flipping through the source material last night, and the juxtaposition is it's jarring. You have Isaac Newton on one page, and a few pages later, a frog that can jump over a minivan. It feels chaotic.
It feels random, but I want to challenge that. I don't think it's random. I think it's interconnected. That frog needs gravity to jump against. That gravity is defined by physics. The physics relies on the matter that makes up the frog. It's a single story, just told from different angles.
I love that. Okay, so let's start at the very beginning. Chapter 1, essentially. The source material kicks off with a section titled, The World of Science. And right out of the gate, it makes a distinction that I think a lot of adults have forgotten since, their school days. Science isn't just a big book of facts you have to memorize.
No, and that is the biggest misconception people have. They think science is a noun, a collection of truths. But science is a workflow. It is a verb. The text defines it as a process where you have to work logically to extract truth from reality. It introduces this hierarchy of ideas, starting with the theory.
Okay, let's unpack theory. Because in casual conversation, at a bar, if I say, I have a theory about who stole my sandwich from the break room fridge, I basically mean I have a hunch.
Right.
Or I have a guess based on nothing.
Right. In common parlance, a theory is a synonym for a guess. But in science, as the text clarifies, a theory is something much, much more robust. It is a rigorously constructed blueprint of an idea. It's you writing down exactly how you think a mechanism works based on observation. It's a model. But here's the kicker. It's worthless on its own. It's just a story until you hit the next step.
The experiment.
The stress test. You have to try to break your own idea. You set up a test to see if the theory holds water. And the result of that experiment does one of two things. It either proves the theory great, you were right, or, and this is the phrasing I really enjoyed in the source material, it shows you something interesting.
Interesting. That is such a polite scientist code word.
It is, isn't it?
It basically means I was completely wrong, but what just happened was cool.
Precisely. Interesting is where discovery happens.
Oh.
Penicillin was interesting.
Right.
X-rays were interesting. Most breakthroughs happen when an experiment fails in a useful way. The source really emphasizes that science is about that loop. Theory, experiment, result. And then you do it again, repeat.
Speaking of breakthroughs, the source highlights the giants who built this workflow. You can't talk about the foundation of science without Isaac Newton. The text puts him in the 1660s.
The apple guy.
The apple guy. But reading this, I realized I've kind of trivialized him in my head. We tell kids the story. Apple hits head, Newton rubs his head, says eureka, and gravity is discovered.
Right, the cartoon version.
But the source points out that the insight wasn't that things fall.
No. Think about it. If you dropped a rock on your foot in 1650, 10 years before Newton, it still hurt. Everyone knew things fell. If you tripped, you hit the ground. That wasn't a mystery. Newton's insight, the universal theory of gravity, was that the force pulling the apple to the ground is the exact same force keeping the moon in orbit around the Earth.
He connected the terrestrial to the celestial.
He unified the physics. Before Newton, people honestly thought the heavens operated on different rules than the Earth. The stars were divine, perfect, unchanging. The Earth was messy and heavy. Newton said, no, it's all the same math. That is a mind-bending shift for the 17th century. It basically demystified the universe.
Wow. And then you fast forward a few hundred years, and we get Albert Einstein. The text calls him the most famous scientist of all, which is a pretty heavy title considering Newton is on the list.
It's earned, though. He lived from 1879 to 1955. And while Newton told us how things move, the mechanics of it, Einstein's theories, specifically relativity, helped us understand the structure of the universe itself. Time, space, energy.
Big stuff.
He was looking at the very fabric of reality. The text notes his brilliance in math allowed him to see structures that were invisible to the naked eye. He was visualizing 4 dimensions while everyone else was stuck in 3.
And speaking of seeing the invisible, we get a little shout out to William Röntgen.
Ah, the discoverer of X-rays.
Which fits perfectly into this theme of perception, doesn't it? Newton tells us why things move, Einstein tells us what reality is made of, and Röntgen gives us a tool to look inside solid objects.
It's amazing to think about the impact of that. I mean, before X-rays, the only way to see a bone was to cut someone open.
Right.
Röntgen gave us a non-invasive way to see the structure of life. It changed medicine forever.
And that segues nicely into the next part of the foundation section, the building blocks of matter. If we're going to understand the universe, we need to know what it's made of. The text breaks it down into the 3 states of matter. And it sounds basic, solid, liquid, gas, but the definitions are really, really intuitive.
I love how they break this down. Let's look at solids first. They do not change shape. And the question is why? Well, it's because the atoms are locked in a grid. They're in a crystal lattice.
So like a regiment of soldiers standing at attention.
Exactly. That's a perfect analogy. They vibrate, they hum with energy, but they don't move from their posts. They hold the line.
Like a rock. Or this table we're sitting at. It feels solid because the atoms are they're disciplined.
Right. Then you add energy heat. What happens to soldiers when they get too hot? They break formation.
Huh.
That's a liquid. The text defines liquids by their ability to flow downwards and fill the bottom of a container. The atoms are sliding past each other, tumbling over one another, but they still stick together. They're cohesive.
So they're a crowd, not a regiment anymore.
They're a crowd, exactly. And then you add even more energy.
And then you get gases.
Gases are the anarchists.
Mosh pit of matter.
Exactly. They have so much energy that they break all bonds. They fly apart. The text notes that a gas doesn't just sit at the bottom of a jar. It expands to fill the entire container. It's trying to escape. It pushes against the walls. That's pressure.
It's wild to think that the only difference between a block of ice, a glass of water, and a cloud of steam is just how excited the atoms are. It's the same stuff, just dancing at different speeds.
That's it. It's just energy levels. The fundamental particles are identical.
The source also spends some time on the tools we use to see this stuff. We mentioned X-rays, but the microscope gets the spotlight here. And there's a description of looking at a drop of blood that I found really evocative.
It's a whole universe in a droplet, isn't it? When you look at blood with the naked eye, it's just red liquid. It looks uniform, homogeneous.
Just red.
But under the microscope, suddenly you see this incredible ecosystem. You see the red blood cells, which look like little donuts, and their job is to carry oxygen. And then you see the white blood cells, these bigger blobby things, hunting for intruders like little amoebas.
The security guards of the body.
Exactly. And it just reminds you that smooth surfaces are an illusion. Everything is granular if you look close enough. The world is made of tiny, tiny things.
And that granularity is a perfect transition. We're going to take that imaginary microscope and zoom in on a specific class of animals, The source dedicates a significant chunk of real estate to amphibians.
Which is a fascinating choice for a deep dive. I mean, amphibians are often the overlooked middle child between fish and reptiles.
Cool.
They aren't as majestic as lions or as scary as sharks, but biologically, they are absolutely incredible.
So amphibian. The word itself means double life, right?
It does. We're going back to the Greeks again. Amphi, meaning both, and bios, meaning life. These are frogs, toads, newts, salamanders. And the defining characteristic, according to the text, is that tether to the water.
Ah, right.
Most can live on land, they have lungs, they walk, but they must return to the water to reproduce. They cannot escape their origins.
It's like they never fully committed to the dry land upgrade. They bought the land package but kept the aquatic subscription active just in case.
They kept a foot in the door of the ocean, yes. And that creates a very specific vulnerability. Their eggs don't have hard shells like chicken eggs or reptile eggs.
Oh, right.
They're soft, they're gelatinous. If they laid them on land, they would just dry out in an hour, so they have to go back to the pond, back to the ancestral home.
The most famous example of this double life is the metamorphosis, the tadpole journey. The text breaks it down into 4 stages, and honestly, when you strip away the familiarity of it, because we all learned this in 2nd grade, it's absolute sci-fi body horror.
It is a total biological reconstruction. You are taking a creature built for one environment and retrofitting it for a completely different one while it is still alive. It's like turning a submarine into a Jeep while you're driving it.
Okay, let's walk through the stages as the source describes them. Stage 1, frog spawn.
The text calls it slimy, jelly-like stuff. And that's accurate. It's thousands of tiny black eggs floating in this protective goo. It's communal. It's an external womb, really.
And then stage 2, the tadpole hatches.
Which is, for all intents and purposes, a fish. It has a round body, a long tail for swimming, and gills. It breathes water. It has no concept of air or legs. It eats algae. It is a fully aquatic creature. If you took a tadpole out of water, it would die just like a goldfish would.
And then the programming changes. The whole operating system gets an update. Stage 3, the transition.
This is where it gets weird. Tiny little back legs sprout. Then the front legs. But the tail doesn't just fall off, it begins to shrink. And the text explains it's actually being absorbed back into the body as fuel.
Wait, really?
Yes. The tadpole is eating its own tail from the inside out to get the energy to build its legs. The gills disappear and lungs develop inside the chest. The mouth changes shape. The digestive system retools itself to eat insects instead of algae. Imagine if you started growing scuba gear and fins while walking down the street. That is what is happening to this animal.
That is bizarre. And then finally, stage 4, the baby frog, or froglet.
Ready for land. The whole process takes just a few weeks. It's a rush job by nature because being a tadpole is dangerous. Everything wants to eat you. Fish, birds, insects. The sooner you can hop out of that pond, the better your chances of survival.
Now, I have a confession. I am in my 30s, and until I read the source material, I still struggle to tell a frog from a toad. I know they're different, but I couldn't tell you why. The source gives us a cheat sheet, though.
It's a very common confusion because they are cousins. They're both amphibians, both anurans. But the rule of thumb in the text is a good one. Frogs are the athletes, toads are the tanks.
Okay, explain that. I like that.
Frogs usually have smooth, wet, slimy skin and very long, powerful back legs. They're built for explosive movement, leaping, and swimming. They are streamlined,
Sleek.
sleek. Toads, on the other hand, are the bumpy ones, warty, dry skin, and they have shorter, stubbier legs. They don't jump so much as they crawl or do little hops. They're built for digging and durability, not speed.
So a frog is a sprinter, a toad is a hiker.
That's a great way to visualize it, yes.
But the encyclopedia vibe really shines when we get into the specific species. It's not just here is a frog, it's here are the weirdest, most specialized frogs we could find. First up, tree frogs.
Amazing engineering here. If you want to live in a tree, gravity is your enemy. You're wet, you're slippery, and you're high up. So they evolved these incredible sticky pads on their toes. They're basically suction cups.
So they can climb glass.
They can climb glass. But the text also mentions a detail I love. Their eyes. They are forward-facing.
Why does eye placement matter for a tree frog? That seems like a small detail.
It's a huge detail. If you have eyes on the side of your head like a rabbit or a deer, you have a wide field of view to see predators coming, but you can't judge distance well. You have poor depth perception.
Right.
If you have eyes facing forward like a human or a hawk or a tree frog, you have binocular vision. You can triangulate. If you are jumping from one leaf to another 50 feet up in the canopy, you really, really need to know exactly where that landing zone is. Missing is not an option.
It's high-stakes parkour. Okay. Then we have the poison dart frog.
The fashionista of the rainforest. The punk rocker.
Bright neon colors. Yellows, blues, reds. Which isn't to attract a mate, right? It's a warning label.
It is what's called aposematism. That's the biological term. It's the frog broadcasting a message to every predator in the jungle saying, I am not hiding from you because I don't need to. I am bright red. I am easy to spot. But if you eat me, you will die. It's an aggressive confidence.
It's the ultimate bluff, except it's not a bluff at all.
Not at all. Their skin secretes some of the most potent neurotoxins in nature.
But my favorite stat in this entire section, maybe the whole source, is the African sharp-nosed frog. This thing is the Michael Jordan of amphibians.
Michael Jordan wishes he could do this. The stats are ludicrous. The source says this frog can leap more than 5 meters in a single hop.
That's 16 feet.
16 feet. For context, that is roughly the length of a large minivan or a small bus.
Wow.
Imagine a creature the size of your hand clearing a bus in one jump. The power-to-weight ratio is just, it's off the charts. If a human to jump like that, proportionally, we would be jumping over stadiums.
That's insane. And on the weird side, we have caecilians. I had to look this up. These things, they do not look like frogs.
No, they look like giant earthworms or small snakes. But they are technically amphibians. They lost their legs entirely over millions of years of evolution because they just didn't need them for their lifestyle.
They use their heads as shovels.
Yes. They have these reinforced bony skulls. They're burrowers. They live underground, digging through mud and leaf litter to find insects and worms. It just shows you how diverse evolution can be. You start with the same amphibian blueprint. One lineage goes for jump over a bus, and the other goes for turn into a worm and dig a hole.
Nature really does just throw spaghetti at the wall to see what sticks, doesn't it?
And speaking of sticking, we have to mention the newts and salamanders, the flick and stick hunters.
The tongue mechanic.
Right. We think of it as a cartoon trope, the frog catching the fly with its tongue, but it's a highly efficient hunting strategy. You don't have to chase the fly. You don't have to expend energy running. You just sit very, very still and launch a sticky projectile at it at incredible speed. The text mentions they also hunt worms and slugs at night, but that tongue is the star of the show.
So we've covered the microscopic blood cells. We've dissected the frog in the pond. Now I want to zoom out. I want to look at the blue parts of the map. Section 3, seas and oceans.
The blue marble.
The source drops the big number immediately. More than 2/3 of the planet is water. 71%, to be precise.
And it introduces a concept that I think is really important for understanding Earth as a system, the world ocean.
Right. We tend to name them separately. Atlantic, Pacific, Indian, Arctic, Southern, like they're separate lakes.
Exactly. We draw lines on maps, but the water doesn't care about our lines. It's one continuous, connected body of liquid. A drop of water in the Arctic can eventually find its way to the Southern Ocean. It's a single, global system. The currents connect everything.
But the Pacific is the big daddy. It's the undisputed champion.
It covers 1/3 of the Earth, just the Pacific Ocean. If you look at a globe from the right angle, basically staring at Hawaii, you can barely see any land at all. It's just an eyeball of blue. It's so vast it creates its own weather. It regulates the planet's temperature.
Now, here's the question that I think every kid asks, and honestly, most adults probably can't answer correctly. I know I was a bit fuzzy on it. Why is the sea salty?
It is a classic question, and the intuitive guess is that it just is. Or maybe that the salt comes from the bottom of the ocean, from vents or something. But the source gives the geological explanation. The salt comes from the land.
From the dirt.
From the rocks, specifically. Think about it. Rainwater falls from the sky. It is fresh water, but it's very slightly acidic because it picks up carbon dioxide from the air.
Okay.
It falls on the mountains and plains, and it slowly erodes the rock. It dissolves tiny amounts of minerals, salts, sodium, chloride, magnesium. That water then flows into streams and then into rivers.
But rivers aren't salty. I've swam in rivers. They taste like mud, not salt.
They are salty, but just very, very slightly. The concentration is far too low for you to taste. But all those rivers, the Amazon, the Nile, the Mississippi, the Yangtze, they all dump that slightly mineral-rich water into the ocean.
Ah, I see where this is going.
Once the water is in the ocean, the sun hits it. The water evaporates to make clouds and rain again. But here's the key. The salt doesn't evaporate, it gets left behind.
So it's a concentration game. The water leaves, the salt stays, over and over.
Exactly. Over millions and millions of years, the salt builds up. The ocean is basically a billion-year accumulation of dissolved mountain runoff, and the text notes, it is the same sodium chloride you put on your fries.
We are seasoning our dinner with dissolved geology. I love that.
The text also emphasizes that the ocean is alive in terms of movement. It's not a stagnant pool. It is a churning, chaotic engine.
We have currents, waves, and tides. What's the distinction the source draws between them?
Okay, so waves are the most obvious. They're surface level, usually wind-driven. You see them at the beach. Tides are gravitational. It's the moon pulling on the water, causing the daily rise and fall of sea level.
Yeah.
But currents, that is the big machinery.
The dump stuff.
The deep stuff. Currents are great bands of water flowing like rivers inside the sea. The Gulf Stream is the most famous example.
So they're like the planet's HVAC system.
That's a perfect way to put it. They move warm water from the equator up to cold places, and they bring cold water from the poles down to warm places. They are the planet's circulatory system. Without currents, the equator would be unbearably hot, and, Europe would be a block of ice.
And deep down in that HVAC system, we have life. The source zooms in on coral reefs. It describes them as these chaotic, colorful cities.
And color is used differently there than on land. We talked about the poison dart frog using color as a warning. In the reef, fish often use color for camouflage. It's so visually noisy down there with the corals, the sponges, the anemones, that being bright orange might actually help you blend in.
Right, hiding in plain sight.
Hiding in plain sight, or of course for warning. The rule is if it's super colorful and slow-moving, it's probably poisonous.
Unless you're a shark. The text mentions the blacktip reef shark.
The apex predator. Streamlined, fast, efficient. It doesn't need to hide as much as it needs to hunt. It's the top of the food chain in that ecosystem.
There's a funny little note in the text about humans here. It says, humans use flippers to swim underwater, mimicking aquatic life.
It's a little reminder of our limitations, isn't it? We are great on land, but to enter the ocean, we have to use technology to fake it. We strap plastic fins to our feet to become artificial amphibians. We are tourists in their world, and we're not very well equipped for it.
Okay, let's dry off. We're moving from the wettest places on Earth to the driest. Section 4. The extremes of land. Deserts and grasslands.
Contrast is the best way to learn. We go from water everywhere to water nowhere.
Let's start with deserts, specifically the sand dunes. The text uses a phrase that actually gave me the creeps. Dunes creep.
It is an ominous image. We think of a hill as a static thing. A hill sits there, but a sand dune is just a huge pile of loose rock fragments. When the wind blows, the sand grains tumble over the top, rolling down the other side, so the whole mountain of sand moves, grain by grain.
The source says some of these dunes are 200 meters high. That's a 60-story building made of sand moving across the landscape.
And the text explicitly says they can bury whole villages.
Okay.
It's a slow-motion tsunami of sand. It reminds us that the Earth is not just a stage we stand on, it is an active participant. It can erase us if we aren't careful.
But even in the desert, there is structure. We get a mention of buttes.
Flat-topped rock formations, the classic Western movie backdrop. The Mitten Rocks and Monument Valley are the example given. These are the hard bones of the Earth left behind after the softer rock and sand around them eroded away over millions of years. They are survivors.
How does anything survive in a place that is actively trying to kill you with heat and thirst?
Adaptation. Extreme adaptation. The cactus is the master of this. The saguaro cactus, mentioned in the text, is basically a biological water tank. It has a thick, pleated stem that can expand to store huge amounts of moisture when it rains.
And it has spines instead of leaves.
Right. And that's a 2-for-1 deal. The spines stop animals from eating it, obviously. That's defense. But they also serve a preservation function. Leaves have pores. They sweat. They lose water through transpiration. Spines don't. By ditching leaves, the cactus seals itself up. It's a fortress of water.
And the animals. The camel gets the spotlight.
The ship of the desert. Their adaptations are incredible. They can go for days without food or water. Their humps store fat, not water, which is a common misconception. They can metabolize that fat for energy and water. They have wide feet that don't sink in the sand, long eyelashes to keep sand out of their eyes.
They're purpose-built.
It's the perfect biological technology for that environment. That's why humans domesticated them. You can't drive a horse through a sandstorm. It will die. A camel walks right through.
Humans adapt, too, in our own way. The text talks about nomads. If the dunes are moving and the water is scarce, you can't build a brick house.
You have to be mobile. Your entire lifestyle has to be fluid. The source describes tents that are easy to pack up and move. You wander to find resources. It's a lifestyle dictated entirely by the climate. You follow the water and the grazing lands.
Unless you find an oasis.
The exception that proves the rule. These are places where deep underground water from an aquifer seeps to the surface, and suddenly you have palm trees, you have shade, you have life. It's a miracle in the middle of the furnace, a pocket of paradise.
From the sand to the dust, let's talk grasslands.
The dusty plains. The definition here is interesting. It's a middle ground. It's too dry for a dense forest. Trees need a lot of consistent water, but it's wet enough for grass to thrive. So you get these endless oceans of green and gold.
And the names change depending on where you are. I love this linguistic geography. It shows how different cultures independently name the same phenomenon.
It's great. In North America, we call them prairies.
Which we mostly turn into wheat fields, right?
Yeah, right. Wheat is just a type of grass, after all. We just swapped the wild grass for a domestic grass that we can eat. In South America, they are the pampas, famous for the tall pampas grass. And in Africa, the most famous of all, the savanna. Same biome, different branding.
The wildlife in the savanna is the classic safari lineup. Herds of zebras, wildebeest, impalas, elephants, giraffes. The text notes they all gather at water holes.
Because water is the limiting factor. In the dry season, it forces a truce, or at least a tense congregation. Everyone has to come to the pub eventually, even your enemies.
But the South American pampas has some creatures I wasn't as familiar with. The giant anteater.
A bizarre animal. It looks like a mistake. Huge, bushy tail, a long snout like a vacuum cleaner hose, and these massive claws for tearing open termite mounds.
And the vizcachas.
Burrowing rodents. They look a bit like chinchillas or rabbits with long tails. They live in these large social colonies called vizcacheras.
And rheas, which are flightless birds, like ostriches.
A very similar niche, yes. They're related. Big running birds.
No.
When you live on a vast, flat plain, you don't necessarily need to fly, but you definitely need to run fast to escape predators.
But overseeing all of this, in every grassland, is the cleanup crew. The vulture.
People usually find vultures repulsive. They are bald, they eat dead things, but the text frames them as absolutely essential. They're scavengers. They soar on heat thermals, using almost zero energy, just riding the hot air, scanning the ground for death.
Grim.
Grim, but necessary. They clean up the carcasses, they process the waste. Their stomach acid is so strong it kills almost any bacteria or virus. Without them, the plains would be a festering disease pit. They are the sanitation department of nature.
So we've covered the natural world. The frogs, the oceans, the deserts, the vultures. Now I want to shift to the human layer. Section 5 is about mapping the human world.
This is where we impose our order on the planet. We draw lines on the dirt and call them countries.
It starts with a really basic but important distinction. The difference between a globe and a map.
It sounds obvious, but it has huge implications for how we see the world. The globe is the truth. It shows the ball shape of the world. The proportions are correct. Africa is huge. Greenland is smallish. But you can't put a globe in your pocket. You can't navigate a city with a globe.
Right. It's not practical.
So we make maps.
Which is what happens when you stretch the world out flat.
And the text implies the problem there. Distortion. You cannot flatten a sphere without stretching something. It's like trying to perfectly flatten an orange peel. It tears or stretches. That's why Greenland looks gigantic on some maps, as big as Africa, when it's actually much, much smaller. The map is a compromise. It is a lie we agree on for convenience.
The source talks about how we make these maps. It used to be drawn by hand guys on wooden ships, sketching coastlines, guessing at what was inland.
Here be dragons.
Exactly. Now, it's planes and satellites taking high-resolution pictures, feeding that data into computers. It's gone from art to precision data science. We know where everything is down to the inch. And we use grids. The text gives the example of using letter and number grids, like finding something in square 4C to locate a street or a park.
It's a coordinate system. It's a way of turning physical space into math. Without grids, you can't have a functional city. You just have a pile of houses. The grid lets you say, I'm here and you are there. It's fundamental to organization.
Speaking of landmasses, the source brings up continental drift. This circles back perfectly to our theme of a dynamic Earth.
This is the slow-motion version of the creeping sand dunes. 200 million years ago, all the land was one supercontinent, Pangaea.
All mashed together.
All one big jigsaw puzzle, and then the tectonic plates started to break up and move.
They split and drifted.
The Atlantic Ocean opened up like a zipper. India crashed into Asia, creating the Himalayas. And they are still moving today. We are moving right now. North America is drifting away from Europe at about the speed your fingernails grow.
There's an interesting note here about borders. We talk about how humans draw lines, but the text mentions that natural borders are often formed by rivers, mountains, and seas.
It makes sense. If you are a king in the Middle Ages, where does your kingdom end? It ends at the big river you can't easily cross, or the mountain range you can't climb. The geology dictates the politics. The map of the world looks the way it does largely because of where the mountains and rivers happen to be.
But then we have the hierarchy of how we organize ourselves. World, continents, countries. The text says there are more than 190 countries.
And the extremes of size are just as dramatic as the biological ones we talked about. We have the whales of countries and the plankton of countries.
Oh, absolutely. On one end, you have Russia.
The behemoth. 17 million square kilometers. It stretches across 2 continents, Europe and Asia. It has 11 time zones. You can have breakfast in Kaliningrad while people are sitting down to dinner in Vladivostok in the same country.
And on the other end, Vatican City.
In the middle of Rome. It's a sovereign nation, but it has a population of about 1,000 people. It sits on a single hill.
It's a country that's smaller than a golf course. It's tiny.
It really shows how flexible our definition of country is. It's not about size. It's about political recognition. It's about a shared idea.
We also get a tour of capital cities. The text defines a capital as the seat of government and lawmaking. Buenos Aires, Moscow. But it also mentions the urban giants, São Paulo in Brazil.
Listed as the world's 4th largest city with 18 million people.
18 million people. That is hard to visualize.
That's a staggering number of humans in one place. These megacities are the human equivalent of the coral reef's dense, complex, layered habitats where millions of individual lives overlap and interact.
And Singapore gets a mention for its modern skyline.
Verticality. When you run out of land, the only place to go is up. You build into the sky. Singapore is a testament to human engineering and organization.
Okay, we are coming into the home stretch, Section 6. The source material has a section that is essentially the Book of World Records. This is the lightning round of Earth's extremes.
I love a good leaderboard. Let's do it.
I'm going to throw a category at you, and you give me the winner, according to the text. No hesitating.
I'm ready.
Hottest place on Earth.
Delol, Ethiopia.
Coldest place.
The pole of inaccessibility, Antarctica.
Which, by the way, is the coolest name for a location ever. The pole of inaccessibility.
It sounds like where the villain lives in a fantasy novel. It's the point on the Antarctic continent that is furthest from any ocean. It is brutally, unimaginably cold.
Rainiest place.
Mount Waialao in Hawaii.
Criest place.
The Atacama Desert in Chile. Parts of it have gone decades without a single drop of recorded rain. It's as close to Mars as you can get on Earth.
Windiest place.
Commonwealth Bay, Antarctica. Antarctica is really sweeping the miserable weather categories here.
It really is. Largest island.
Greenland. Australia is usually counted as a continent, so Greenland takes the prize for island.
Highest mountain.
Mount Everest in the Himalayas. The roof of the world.
Longest river.
The River Nile in Africa. Though I know Amazon researchers might argue that point, the text gives it to the Nile.
And finally, largest lake by surface area.
Lake Superior in North America.
It's quite a list. When you hear them back to back like that, you realize just how diverse and, well, violent this planet is. You have places that will burn you, freeze you, drown you, and dry you out.
It is a planet of extremes. We happen to live in the temperate, comfortable middle zones mostly, so we forget how hostile the edges really are.
So let's unpack this. What does all this mean? We've gone from a single cell under a microscope to the borders of Russia. We've looked at frogs jumping over minivans and dunes burying villages.
I think the core takeaway is exactly what we hinted at in the beginning. The world is dynamic. Nothing is static. Not a single thing.
It's all moving.
It is all moving. The continents are drifting apart right now as we speak. The sand dunes are creeping forward. The water in the ocean is flowing in great currents. The tadpole is dissolving its own tail to grow legs. Even the atoms in the solid rock of Mount Everest are vibrating.
It makes you realize that the encyclopedia isn't a book of fixed facts. It looks like it is because it's printed on paper, but it's actually a snapshot of a movie that's still playing.
That is a beautiful way to put it. We are freezing the frame to study it, but the movie keeps running whether we're watching or not.
And here's where it gets really interesting for me. The final provocative thought. If the continents drifted apart over 200 million years, and we know those sand dunes can bury villages today, what does the map look like tomorrow?
That is the question. The globe we look at today, that familiar arrangement of 7 continents and 5 oceans, it's just temporary. It's just the arrangement right now, a geological snapshot.
If we could fast forward 1 million years, which is nothing in geological time. The map would be wrong. The snapshot would be outdated. Africa might continue to split apart. The Atlantic will get wider. The Pacific will shrink. The Mediterranean might close up entirely and become a new mountain range.
It's a humbling thought, isn't it?
Yeah.
We are just passengers on a very, very slow-moving ride.
We are indeed. And science is just our attempt to keep a logbook of the journey.
Well, that wraps up our deep dive into the world of facts, amphibians, and shifting sands. It's been a journey across the entire spectrum of knowledge.
It has. Always a pleasure to explore the microscopic and the monumental with you.
Thanks for listening, everyone. Keep curious, keep learning, and remember, even the ground beneath your feet is going somewhere. We'll catch you on the next deep dive.